Okay, so why don't we get started? We'll start with some announcements. There is a lab due tonight. I think all of you know that already. Okay, so make sure you turn it in and then spend the rest of the week focusing on the exam, because we do have a midterm exam on Friday. Okay, so as I had announced earlier, and it's also posted on the class webpage, all students who are in the Amherst area, regardless of section, will take the test in person. Okay, even if you are in the online section, you're in the UWW section, you take the test in person unless you are an off-campus student, you don't live in the Amherst area. Okay, so for all of you, you have to come to the exam room, which is in the ILC. Okay, the exam room has been posted on the course webpage. I'm going to send an email with all of the details. Okay, so the exam will be an evening exam, 7 p.m. this Friday, 7 to 8:30. Okay, it's a closed book, closed notes exam. Okay, so you can't bring any material with you. But of course, if something is not clear during the test, you can ask a question. We will be there. All right. I have already posted a sample exam from last year with the solutions. Okay, it's on Moodle. I put a note on Piazza as to where to find it. Make sure you take a look at it just to get some sense of what kinds of questions to expect, approximately how many questions to expect. And so there should be plenty of time. Typically, it doesn't take 90 minutes to finish the test. If you know the material, you can get it done faster. Okay, so that should be enough time to finish whatever is going to be on the test. Okay, lectures 1 through 8 is part of test 1. Okay, then the next 8 lectures will be test 2, and the last 8 or 9 lectures for the final exam. Okay, any questions about the midterm exam? Yeah, I'll send an email with all of the details again, and we'll also post it on Piazza. If any questions come up, please send me a message on Piazza. Okay, so why don't we get started? Since we are starting, you have to turn your laptops off. Okay, the two of you are sitting in the front. All right. Okay, so we will switch gears and talk about different topic today, which is scheduling. Okay, we'll talk mostly about distributed scheduling and cluster scheduling. But just to set the ground first, I'm going to talk about scheduling in operating systems as they relate to things like multiprocessors. Okay? So I'm assuming uniprocessor scheduling is something you already learned in an undergrad OS class, so I'm not going to cover it again. Okay? So we'll talk about multiprocessors, how do you schedule multiprocessors, okay, or schedule processes on multiprocessors. Then we'll talk about distributed scheduling. How do you schedule tasks on a group of machines? And then we'll generalize that to cluster scheduling, okay, which is a specific form of distributed scheduling. Okay. So let's start with multiprocessor scheduling. Okay, so here's a picture. It's a little abstract, but that's a picture of what a typical multiprocessor machine looks like. As the name multiprocessor suggests, there is more than one processor or core on that machine. Okay, those are the boxes at the top with the blue circles in them. Okay, we'll assume that each of these cores has some caches associated with them, the cache and the L2 cache and so on, that are used to speed up performance of anything that's executing on those processors. Okay? And then you have a system bus that's shown by that blue line, the horizontal blue line, that interconnects all of these processors. And then you have memory. Yeah, memory banks that essentially store your data and programs. Okay, so that's a picture you want to keep in mind. And I'm going to, excuse me, come back to why this picture matters from a multiprocessor standpoint. Okay, so the thing you want to keep in mind is some of these caches are going to be shared and some are dedicated to processor. Okay, so in particular, what we have shown here is the L2 cache and the L1 cache are dedicated to a processor, but other caches may be shared. Okay, so how do we go about scheduling tasks onto multiprocessors? There are two pictures that are shown here. One is called a centralized queue. The other is called a distributed queue. So what does this mean? Okay, so let's assume you have a set of processors and the operating system wants to schedule threads or processes on those processors or cores. So we'll assume that all of the processes or threads that are wanting to run are going to be in a queue. Okay? We'll call this the run queue. Okay? And we will assume that whenever a processor becomes idle, okay, when a processor becomes idle, it's going to look at this queue and take a process or a thread from that queue and execute it. And we'll assume that execution happens one quantum at a time. A quantum is a time interval. Okay? Once you run a process, it can run for up to a quantum, then it has to give up its the processor, and then the processor goes and picks the next job being a process or a thread from the queue and so on. Okay? So this is a very simple way to do it. This is essentially what happens in uniprocessors. There's a run queue. There's only one processor there or one core, and you can just take threads or processes from the queue and then you schedule them, and you can do round robin or whatever else you want to do in terms of policy. Okay? So that's our centralized queue. Okay, now, if as you have multiple processors here, okay, you can have a scenario where two or more processors become idle at the same time. Okay? So they all want to pull a job from the queue to run. Okay? The queue is a shared data structure, so it has to be protected by a lock, okay, because you can only have one processor essentially get access to the queue at any given time. So essentially it's going to become a bottleneck very quickly, because you might have a case where one processor is trying to pull something off the queue, another processor is waiting because it can't even get the lock, so it cannot do what it needs to do. Okay? So you will have essentially the queue becoming a bottleneck if you have lots of processes. If you have only 2 cores, maybe it's not a big problem. If you have 16 cores, it can become a problem. Okay? So that's a centralized queue. So you can say, why do it that way? Why not have more than one queue? Okay? In the limit, you will have 1 queue per core or 1 queue per processor. Okay? This is a distributed queue. In this case, when a job arrives, which is a process or a thread, you're going to assign it to some queue. Maybe you'll say, put it in the smallest queue. Okay? So it will join that queue, and then that processor can simply take jobs from its local queue and schedule them one quantum at a time. Okay? This is the other extreme, the centralized queue, distributed queue. Now this is showing a scenario where one queue is shared by 2 processors. Okay? You could have essentially a queue per processors or queue for every 2 processors, any model that you can think of, but the point is you have more than one queue and the centralized approach. Okay? Now in this case, you will no longer have the problem of the queue becoming a bottleneck because you have 1 per processor. Okay? So you will not have that problem. Okay? But you will have other problems. The other problem being that some of these queues might have fewer tasks than others. So there is imbalance. Okay? So say that the first queue has only 2 threads and the second queue has 16 threads. Okay? It's clear that the one that has fewer threads, those threads will get more CPU time than the others because you're doing round robin. So some threads or processes might get less CPU time simply because they landed in a queue that has a higher number of tasks than others. Okay? So you might have to periodically go and rebalance these queues if there is imbalance that is seen. Okay? Otherwise, you will not get a good performance in your overall performance in your system. Okay? Now, the other problem that I'm not yet mentioned is that of cache affinity. Okay? So what does cache affinity mean? So essentially, when you run a thread or a process on a particular processor, okay, that processor is going to fetch its instructions and data from memory and keep it in its cache, whether it's L1 cache or L2 cache and so on. Okay? And this speeds up the execution of the process because otherwise you are going to have cache misses and you got to fetch this instructions or data from RAM, which is much slower than if it was already in your cache. Okay? So if you execute with a warm cache, your performance is going to be much better than if you execute with a cold cache. Okay? And that's the whole reason you have these L1 and L2 and L3 caches is they essentially have the instructions and data for any process that has executed in them, so that next time you execute, because you might already have all of the instructions or data, you will have better performance. Okay? Now consider what is going to happen if you have the a centralized queue. Okay? Suppose that a thread is going to run on core 1. Okay? and then essentially all of its instruction, not all, but its hot instructions and data are now in that cache for core 1. Okay? And it goes back to that end of the queue once it's done, and the next time it's scheduled, it gets assigned to core 3. Okay? Now core 3 has not executed this thread or process before, so it has a cold cache. So you are going to essentially see a lot of cache misses. Okay? And then your cache gets warmed up. Okay, quantum ends, you go back to the queue, and then you get assigned to yet another core. Okay? Because you can't control which core is going to execute this process the next time it gets to run. It's going to get assigned to whoever is idle when you're at the head of it. Okay? So you are going to essentially have what is called poor cache affinity. Your cache affinity essentially says you should try to schedule a process on the or a thread on the same processor it executed last, because you will again run with a warm cache. Okay? And that's important for performance reasons. Okay? Now, in the centralized queue, you will essentially not have this load imbalance problem that you have here, because it's only one queue. Whenever there are tasks, they'll get to run on cores, but you will have poor cache affinity. Okay? In contrast, in a distributed queue, you will have potential imbalances, but cache affinity problem is not going to be there, because if you have one queue per processor, you're going to run on the same processor over and over again, unless you are moved to another processor for load balancing reasons. But that, let's say, is not a common scenario. It may happen only once in a while, and you can pay the cost of cache misses every once in a while, not every time you get scheduled for the next quantum. Okay? Yes, question. Okay, so question is, what happens if in a distributed queue, some queue has fewer threads and others have more? Is that the same as the centralized case? Is that what you're asking? The centralized queue just says there is one queue. Okay, if there are 10 threads, they're all in that queue. Okay, and they are getting assigned to processors when processors become idle. Okay, now those threads will get split across multiple queues in the second case. How it gets split depends on how they get assigned to queues when they arrive. Okay? If you do a fair assignment, then the queue should be roughly balanced, in which case each of them is going to get equal amount of CPU time. Okay, yes, question. Do queues have limitations? Is that what you're asking? So it's not clear what you mean by limitation. So the centralized queue has a problem of it becoming a bottleneck. Okay? And it has poor process cache affinity, because you can get assigned to different processors. In the distributed version, you are going to get imbalance, but you will not have the contention, because you will not have many processors trying to contend for the queue, and you have better cache affinity. So those are your trade-offs. Okay. Yes. Is the OS a process itself? The OS is a privileged process. It's the kernel that is going to run, right? So okay, question is there a core or that dedicated to process? There is no such thing. The kernel will run on any of these cores. Depends on what is happening. If a process that's running on a core makes a system call, then you will invoke the kernel and the kernel will run. Okay? And so there is no reason to dedicate it to a core. Okay? You can run on any core. Okay, so that's our multiprocessor scheduling. There are many variants of multiprocessor scheduling. Okay, here's one policy. It's called gang scheduling. Okay? It's particularly useful in cases where you have parallel applications or multi-threaded applications is a good example. Okay? So if you have lots of threads in your application, okay, and so gang scheduling says that you can then run these threads on all of the cores all at once, okay, so that all cores are running threads of the same process at the same time. Okay? This reduces waiting times, because if these threads are communicating with one another, okay, since all of them are executing, they can essentially process these messages faster. Otherwise, you might have a thread sent a message to another thread, but the other thread is not yet scheduled on its core. So it will wait until it gets scheduled, and then you have to wait for a response to come back. If you coordinate the scheduling of these threads or parallel jobs on all the cores, so that all the cores run processes of the same job or threads of the same application at the same time, you can actually get some of these benefits. It reduces waiting or blocking time from messaging and things of that sort. Okay. So that is called gang scheduling. Essentially, schedule this group of jobs as a gang on all of the cores at once. That's the basic idea. It's a popular scheduling policy in any parallel applications. So whenever you have machines that are optimized to run parallel jobs, you will see that there are variants of gang scheduling that are run on your processors. Okay. Now, there are some questions that you ask is, what happens if I scheduled n threads of a process on n cores and one of them blocks? Let's say one of them does IO. What should happen to the rest? And because as soon as that blocks, then if you run something else, you're no longer doing gang scheduling, because the assumption is all of the cores are going to run threads of the same process. So there are two ways to address it. One is saying that if one thread or one process blocks, then preempt all of them. Okay? So it's all or nothing. If one of them blocks, you say, okay, quantum is done. Everybody has to relinquish their cores, and then you run the next applications, threads or processes. Okay? So that's the first policy. The second policy says that even if you have a thread or a process that has blocked, and normally you would relinquish the CPU. That's the general assumption. Okay, so you can say, because we are doing gang scheduling, okay, you don't want to relinquish the CPU if other threads can still do useful work. So in that case, you will raise the priority of that thread, so it continues to hold that CPU even though it's not executing. It's blocked for IO or blocked for some other purpose, but other threads that are scheduled as a gang can continue to execute and make progress. Okay? So you have one of these two policies. As soon as something blocks, you can essentially make preempt the entire application, or you say you will not preempt it. You will essentially keep some cores idle just so that you can run the other threads of that process. Okay? So these are the two ways you can essentially address blocking calls that occur in gang scheduling. Yes, question.
Each queue has some threads already scheduled, and they are not equal. Like some queues more threads, some queues less threads. Now, parallel application company schedule it to all n queues. Are they guaranteed to run at the same time? So the queue length is fixed.
Okay. So the question is, in the previous figure that I showed, if you have multiple queues or distributed queue scenario, and they have unequal number of tasks, and there's a parallel application that arrives, okay, how do you guarantee that it's going to get scheduled as a gang? Okay. So one thing I should mention is the scheduling policy either has to be optimized for parallel application or it is optimized for general purpose use. Okay. What I showed here is a general purpose case where you essentially have a laptop with 4 cores. One of them runs a browser, another one runs something else. Your applications are all independent, they're all running. And so that is this case. Okay. Now, if you have parallel jobs, then the entire scheduler is now doing gang scheduling. Okay. So it's not, in that case, you would not use gang scheduling to essentially schedule interactive applications on a device like a laptop. That's a specialized machine that's designed to run parallel jobs. Okay. So it's one or the other. So this is a special case. You will not run other types of jobs in this case, at least not with that scheduling policy. Okay. Yes, question. What are spin locks? Okay. A spin lock essentially means that it's a form of a busy wait. So it's type of a lock. Okay. So you know what a lock is, right? So now there are many ways to implement a lock. One way is to say that while I'm waiting for the lock, I'm just going to sit and spin, which means that I'm just going to keep checking, is the lock available, is the lock available, is the lock available. So I'm polling, I'm wasting cycles, but that's one way you implement a lock. Okay? In some parallel applications, that's how you do a lock. The other way you to do a lock is the lock is not free. You essentially block the process, and the process no longer runs. Okay? So spin lock is a form of busy waiting. Okay? Yes, question.
We have 4 cores and sign for the remaining.
Okay, question is, if you have 4 cores and you have scheduled a process with 2 threads on 2 cores, what do you do with the other 2, right? So the answer is going to depend on what the CPU scheduler is, right? In gang scheduling, you will assume that the core should run threads of the same process. Okay, so you might find another process that does 2 threads and schedule them. So you have one gang on 2 cores, the other gang on the other 2. That's one that you would do. But if it's a general purpose scheduler, you can schedule whatever thread or process is available to run. Okay, there is no reason to coordinate. This is coordinated scheduling. Okay, you can just do uncoordinated schedule, run whatever is available, and then that's the way it is. Okay, so that's multiprocessor scheduling. We are going to switch gears and talk about distributed scheduling. Okay, so now we are going to look at scheduling across machines. Okay, multiprocessor scheduling was still scheduling jobs that are on a single machine, just that there are multiple cores or multiple processors on that machine. Okay, now we are looking at the distributed case. Okay, so first let's talk a little bit about history as to how this occurred. Okay, so distributed scheduling was first designed in the workstation era. That was 1980s, 40 years ago. Okay? And the idea was the following. So we assumed that users had a workstation on their desk, like a desktop. Okay? And workstations were powerful. And it was assumed that not all users might be using their machine at a given time. Maybe some users are not in their office. They've gone to a meeting, okay? Or they've gone for lunch. Okay? So there may be machines in your environment that are sitting idle. Okay? And machines in those days were still expensive. So the question was, could you make use of idle machines somehow, and how could you put them to better use? Okay? And the idea was, if there are some machines in your network that are overloaded, and there are other machines that are sitting there idle because their user is not using their machine, why not move some jobs from the overloaded machines to another machine and make use of those idle cycles, because they're wasted anyway, right? So if you start 10 jobs on your, or 10 applications on your machine, your load on your machine might go up. Okay? But there may be several other machines in the environment. The users are not using them and they're sitting there idle. So your machine could offload some work to those other idle machines and make better use of CPU cycles in your environment. Okay? So that was the reason this notion of distributed scheduling was invented. Okay? So the basic reason, early reason, was to harness idle cycles on workstation. If there are idle machines, let's put them to use. Okay? Overloaded machines can then send work to this idle machine. Right? That way all jobs get to run faster, because you can essentially get better throughput from your system. Okay? So this was referred to as scheduling in a network of workstation. Okay? And that network of workstation had an acronym called NOW, not used anymore, but used in those days. Yeah. So the idea was users would start jobs on their machines, okay? Like normal. You can start a simulation, you can start your browser, or like browsers didn't exist in those days, but some application. Okay? And so then the OS would then schedule them normally. Okay? But if the OS found that the load on that machine was high, it could go and look for idle machines in the environment and essentially offload some tasks. Okay? That essentially was the concept of distributed scheduling. So now you no longer take a process and schedule it on process cores of that machine. You can take a process and schedule it on some other machine. Okay? So that's the basic idea. Okay? Now, before we think about how to do this, we should ask the question, is this actually a useful thing to do? Yes, your question. Okay. Question is, if the process is going to do I/O to files on the disk, then can you run it somewhere else? That's your question, right? So the assumption here, we didn't talk about a lot of the underlying assumption. The assumption here was the file system also was distributed. So all files were accessible on all machines. They look identical. Okay, so any files that are on one machine can also be accessed on another machine, because they are all. So think of that one way is all files reside on the server, and every machine has simply mounted them from the server. So then it doesn't matter where you run, because every machine sees the same set of files. That's one assumption you can make. But otherwise, you cannot just move a job somewhere else if the files are not accessible, if they want to do it. Okay? But we'll get to that. Okay? So the first question to ask is, okay, so you can think about moving jobs to idle machines and so on, but that's going to complicate your scheduling policy. Is this useful, and when is it useful? Okay. So let's try to understand how you can even think about this distributed scheduling scenario from a very simple analysis standpoint. Okay. So we are going to ask the following question, and you will see why this question makes sense. The question is, what is the probability that there is at least one machine idle in your network, and then there's at least one job that's waiting on some other machine? Okay. What's the probability that both of those two events are true at the same time? Okay. And we'll see that the answer to that question actually has direct relevance to distributed scheduling. So I'm going to explain some very basic concept first, then we'll get back to that question. Okay. So first, assume that your entire network has high utilization. All the machines have high utilization. Okay. So then we'll say, now let's suppose that some machine in that network decides that it wants to offload work because it has high utilization. Okay. What are the chances it's going to find an idle machine? Okay. The chances of finding an idle machine will be low because the utilization is high. Okay. So the chances you will actually be able to offload work is not going to be very high because every other machine is loaded. No machine is able to accept work. Okay. So in this scenario, distributed scheduling will not give you any benefit because there is no machine you can offload work to, because all machines are overloaded. Okay. All right. So now let's look at the other case. Let's assume that all machines have low utilization. Okay. Now in this case, there are lots of machines in the network that are willing to accept work because they have low utilization or they're simply idle. Okay. Now, but what is the chance that there is actually a machine that is going to look to offload work? Okay. That's also going to be low because if you have low utilization in your network, okay, the chances are that most machines have low utilization, so there is no work to offload to begin with. Okay. So in this case, it's the opposite, where machines are willing to accept work, but there's no work to offload on average. Okay. So your distributed scheduling is not going to help, okay, because there's nothing to offload in this case. Okay. So when you have low utilization, this whole notion of let's try to find idle machines and offload work doesn't get you anything. Okay. When you have high utilization, also it doesn't get you anything because there are lots of jobs that are willing to be offloaded, but there are very few machines to offload them to. Okay. So in both of these extreme cases, you're not going to see much benefit of implementing distributed scheduling. Okay. So does that mean it's not useful? That's not the case, because there's a middle case where the system has moderate utilization. Okay. So in this case, the chances that there are going to be some machines that have jobs to offload and there are some machines that have idle resources are going to be both non-zero. So this is the only case where you actually will see benefit of implementing distributed scheduling. Okay. So the first thing is it's not always beneficial. There are only certain scenarios, particularly when the system as a whole has moderate utilization, where it's actually useful. In the other two extreme cases of low or high utilization, not going to give you much benefit. Okay. So that brings us back to that question. What is the probability that at least one system is idle and one job is waiting? Okay. So that probability curve is going to look like this, okay, where the x-axis is essentially the load on the system. Okay. So essentially, when the load is low, okay, the probability that a system is idle is going to be high. Okay. The probability that a job is waiting on any system is going to be low. Okay, because job waiting means that machine has to have high load, which is why it's waiting, not running. It's waiting to run. Okay. So you take the product of the two, that number is going to be low. Okay. So it's going to be here. Okay. In the high utilization case, the opposite is going to be true. The probability that a system is idle is going to be very, very small, close to zero. Okay. the probability that a job is waiting is going to be very high, close to 1. But you take the product of the two, again, you're back to 0. Okay? So essentially, that probability curve is going to peak somewhere in the middle, which is what it says, that essentially the middle moderate utilization is where both of those events are true. That is when distributed scheduling helps. Right? There's a job waiting, there's a machine willing to accept it. Okay? There's a simple analysis using probability that basically says that distributed scheduling has utility only in the scenario where the system utilization is going to be somewhere in the middle, neither too low nor too high. Is that clear? Okay. So I'm going to now skip the rest of this analysis. We will look at policies to do this. Okay, so assuming you still want to implement distributed scheduling in your network of workstation, how do you do it? Okay? So there are 4 components to this scheduling policy. Okay? First one is called transfer policy. Transfer policy says when should you transfer a process from the local machine to someone? When should you offload? That's your transfer policy. Selection policy says which process should you offload? If there are many running on this machine, you want to offload somewhere, which one are you going to pick? Okay, that's a selection policy. Okay. Location policy says where do you send that work to? Okay, which machine are you going to offload to? How do you find that machine? That's your location policy. Okay, and information policy says what information should the scheduler keep to make all of those decisions. Okay, so those are the 4 components. I will see that by and large for the transfer policy is going to be threshold based. You have a threshold utilization. Above that utilization, you will say I'm heavily loaded. You might have some low utilization, you're lightly loaded, and so on. Okay. Selection policy will see in most cases you want to transfer a new process that has arrived. You start a job, you basically start it on some other machine. Okay. Transferring running processes is more complicated. Okay, because that requires something called process migration, because you have to essentially take a process that's actually executing and move it to another machine. Okay? That's something that most operating systems will not support even today because it's complicated to do. Okay? So by and large, if you have a new job, you want to submit a new job, okay, you essentially just start executing that job somewhere else rather than create a process and then move that process. That's much more complicated. Okay? Where to transfer is something you have to figure out. You have to either keep load information or you have to query these nodes to find out their current load and so on, and that's how you're going to find it. And information policy will see that you can have a centralized case where you keep all of this information on some central coordinator, or a decentralized case where decision making is done locally. Okay? And we'll look at examples of all of these. Okay? So the first type of policy is called sender initiated. Okay? As the name suggests, okay, essentially when a node becomes heavily loaded, it tries to offload work. So it is the sender. It is sending the task somewhere else. Okay? That's called sender initiated policy. Okay? What's the transfer policy? It's a high threshold T. Okay? If the number of jobs that are waiting, okay, to execute exceeds some number T, then you become a sender. Okay? An alternate way of saying it is you track the utilization of the system. The utilization goes above a threshold, you become a sender. So both are roughly equivalent. Okay? So that's your transfer policy. So whenever the load goes above some threshold D, you are going to become a sender and try to offload. Otherwise, you don't do anything, execute locally. Okay? What's the selection policy? Okay, when you become a sender, you take a job that has newly arrived, hasn't started executing yet, and offload that over jobs that are currently executing. Because the former is going to be much simpler than taking an existing process and moving it somewhere else. Okay? That's the selection policy. Very simple. Newly arrived jobs are the ones that are moved, not existing jobs. Yes, question. Okay. Question is, a newly arrived job, why has it come to a process, not a process, a machine that is heavily loaded? Why did it not go to idle machine in the first place? Okay, the assumption is processes are started by users on their machine. Okay, so maybe there's a user that starts a lot of processes. Okay, so they will all arrive at that machine. Okay, So we assume that users submit jobs on their local machine. Just as you started a browser, you started mail, you maybe started some Java program. You always start them on your local machine. The scheduler can decide to move them somewhere. You don't start job on somebody else's machine. That's the assumption, because the workstation model, each user owns a machine. They use their machine. The OS can decide to run some job somewhere else. Okay. All right. So location policy, how can you decide where to run the job? Okay, you essentially can say random. Random just says you toss a coin and just say, okay, I'm going to move this to machine N. You just pick a machine and move it there. Okay? It's a random policy. It doesn't need any information at all, because you're just randomly sending a job somewhere. Okay? Now clearly that may or may not work, because if you end up picking another machine that is also heavily loaded, you send the job there. That machine is also a sender. It will just bounce the job and try to send it somewhere else. Okay, so your job might keep hopping. Okay, if you just end up sending it to machines that are all heavily loaded, because you're not checking any load information. You're just sending jobs randomly to some machine. Okay? So you might have to limit the number of times the job bounces around if this keeps happening. Okay? A better policy is you actually check the load on machines and then send a job to a machine that is willing to accept that job. Okay? So you can say, I'm going to probe node sequentially and find a machine that has a load of less than T. Okay, above T is a sender, below T it can execute your job. So you can pull a machine, and then if it is load is less than T, you're done. Okay? If not, you go down to the next machine and so on. Okay? That's a sequential policy. Okay? You can, of course, query all of them in parallel, saying ask all the machines, send me your load. They all send your load. You find the one with the least load. Okay? Maybe that's better than just finding the first one that has load less than T. Okay? So you can query in parallel, you can query sequentially, anything you can think of, you can do to figure this out. Okay? A very simple sender initiated policy. Okay. Next is receiver initiated. Yes, question there.
Is it something like scheduling a new thread over?
Okay. Question is, are we talking about scheduling an entire process on different machines? Yes, we are. And the second question is, can you schedule a thread of a process on another machine? No, you cannot. Because the basic assumption is threads within an application share the same address space. So there's no concept of 3 threads of the process run here and 2 other run on some other machine, because they have to share memory. And then that memory resides on one machine. So you cannot simply run them on multiple machines. So essentially you can schedule processes. The process that you are scheduling on some other node can itself have threads. That's not a problem. Okay, but you don't have a concept of I can split the threads of an application and run them. So that doesn't work. Yes, questions? Yeah. Question, that's a good question. The question is the location policy implemented at a machine level where each machine makes a local decision, or can it be implemented globally at, say, a coordinator node or a load balancer that keeps track of every machine's load information and makes the decision? The answer is both policies exist. What I'm showing here is a very simple local decision making. You'll get to centralized decision making, you'll see that there are examples. Okay? So in this case, it's the local machine that is querying. Okay? And it's just trying to find a node to offload. But of course, what you said, of course, has been done as well. Okay? And we'll get to that in 2 slides. Okay? So receiver initiated policy is the exact opposite. Okay? Here, when the load on a machine falls below a low threshold, okay, the machine becomes a receiver. It's willing to accept work from others. Okay? So it's going to go around hunting for work. In the previous case, the senders are looking for machines to offload to. Here, a machine is looking for work to take on. It's the exact opposite of a sender. So now you are a receiver. Okay? So question is, how to implement this? Transfer policy says when the load on a machine falls below a low threshold, it becomes a receiver. tries to find a process or a job from somewhere else to run. Okay? What's the selection policy? Again, you want to take a newly arrived job and start executing. Otherwise, you have to do process migration. Okay? What's the location policy? Okay? Location policy says where are you going to find the work to take on. So you have to find a machine that's heavily loaded somewhere. Okay? So again, you can probe. Okay? You can essentially query n machines and find the most heavily loaded machine and say, send me some work. Okay? So that's your location policy. Okay? You can, of course, query in parallel, query in sequence. Everything we said on the previous slide is still the case. Okay? It's just that rather than trying to find a machine to send work, a machine that's lightly loaded is looking for a machine that has more load and asking to ask for work. Okay? And then you can, of course, have both of those two in parallel, which is called symmetric policy. Yes, there's a question. Okay. What is the selection policy? Selection policy says that if you want to take on work, okay, which type of job will you accept to execute? Okay? So you contact a heavily loaded machines and give me some work. Okay? How do you decide which of its processes you want to take on? Okay? The idea is you typically want to take on newly arrived jobs because you can simply take that command that the user has typed and execute it locally, rather than take a process that's already executing and moving it. That involves process migration. Okay? Yes. Yeah, partially executed means process migration. If it's already started executing, you can still move it somewhere else, okay, because it's not done with the execution, but that requires you to migrate that process that has started executing, okay, which has a lot more complexity than you just take a command and then you say, I'm going to run it somewhere else. Okay. Okay, symmetric policy says that you have both sender initiated and receiver initiated policies executing on all the nodes. Okay? And so there are two thresholds here, a low threshold and a high threshold. Okay? And so if your load goes below the low threshold, you become a receiver. If your load goes above a high threshold, you become a sender trying to offload work. If you're in the middle, you're neither a sender nor a receiver. You just execute your local processes and you neither take on work nor do you send any work. Okay. So now if you become a receiver, you are going to do what I showed in the receiver initiated policy. You'll try to find some node to take on work. Okay. If you are a sender, you will do what I also showed in the sender initiated policy. You'll actively look for nodes to offload work. Okay. Technically, you don't need both, but you can have both in the system if you want to. Okay. So this is called a symmetric policy. So you have these two thresholds, and essentially you decide whether you're a sender, receiver, or neither. If you're a sender, you poll for nodes on a receiver list. Okay. In this case, you're assuming that you have some information about who or what is the load in the system, who is a receiver, who is a sender, and so on. Okay, so senders will poll nodes on the receiver list, receivers will poll nodes on the sender list, looking for work or trying to offload work. Is this clear? Okay. So these are basic concepts. So we'll now look at 2 or 3 actual systems that implemented these ideas. Okay, that way you will see how they made design decisions and how they went around implementing these distributed scheduling policies. So the first one is called the V system from Stanford. These are all very old operating systems. They don't exist anymore. They were designed in the 80s and 90s, but these were the ones that first came up with this idea of distributed scheduling within the OS. Okay, so here the information policy says it's state change based, which means that every time let's say your load goes above a high threshold, you become a receiver, become a sender, or your load goes below the low threshold and you become a receiver, you broadcast this to the entire network saying, I am a receiver, I have become a sender. Okay? So every machine now has some notion of which nodes are receivers, which nodes are senders, which ones are neither, because every time there is a significant change in load on the machine, it's broadcasting this information to every other node, every other machine in the network. Okay? So in this case, you no longer need the central coordinator, because load changes, important load changes are broadcast. So every node can maintain a local table of what is happening in the network in terms of load. Okay? Now, given this load information, we'll assume that M least loaded machines are receivers. Okay? The lowest, the lightly loaded ones are receiver, everyone else is a sender. Okay? And then what V does is essentially is a sender initiated policy. Okay? When you're a sender, you are going to look at your receiver list, which is the M least loaded nodes, because you have this table of everyone's load. Okay? The ones that are at the bottom, they are all receivers. So you are a sender, you're going to look at those M and try to find a node to offload. Okay? So you will take one of these M and probe them randomly and say, are you still a receiver? Okay? If so, you offload jobs. Okay? The reason you probe and not just send the job is some other node might have already sent a job before you, and before that node has broadcast any new information, okay, it may no longer want to receive any more. Okay? So you always check saying, are you still a receiver based on information I have? And if so, you send a job. Okay? So that is what this machine is going to do at the V system. Yes, question. Yes. Yeah, the question is here you have M least loaded nodes are receivers, everyone else is a sender. In the previous case, when I showed the symmetric policy, you had a third case where you are neither a sender or a receiver. In the V system, that third case doesn't exist. You're either a sender or you're a receiver. Okay, so that's their design decision. There's no reason to not have a middle ground, but they didn't put it in. Yes. Question. Okay. Question is M constant? Does it change? What is optimal? So first thing is that you have to decide M based on the number of nodes in your environment. Okay? If you're a 100 machine system, maybe M is 10. I'm just picking a number, not saying that's optimal. But if you're 1,000 machine system, maybe M is 50. Right? So the value of M is in proportional to the size of your system, right? The number of machines in your system. So it's not a arbitrary constant. It has to be determined based on the size of the network. Okay? Now, having said that, for a given size network N, what is the right value of M? That's a good question. I think I don't have an answer to that. I think that was configurable from what I can remember in the paper. We will make the paper available, but I don't think it actually said how to choose M. Left to the system administrator to pick. Okay. Yes. Okay, question is, when you say that the load is less than T, do you estimate how long the process runs and so on? That's your question, right? So typically the OS will not have any information about what the process is going to do. And you submit a job, and let's say you start a browser. Okay, the OS has no idea whether you're going to run the browser for 1 hour, 1 day, 10 days. Maybe you just leave it running on your laptop and it keeps running. So typically we assume that OS does not have knowledge of what the process will do. Okay? Now, of course, you can try to estimate based on past runs of that similar job what might happen, in which case you might have some idea. In this case, we assume you don't know anything. Okay? And then you assume that it's a process, it has some work to do. It could be a long process, in which case you might have offloaded a lot of work to some other node. But when you do that, you don't know that ahead of time. Okay? All right. Second case system is a competing operating system called Sprite, which was developed at the same time as system V. Okay, so essentially this idea of distributed scheduling came about in both of the systems more or less at the same time. They were being developed for this network of workstation environment. Okay. So there are some differences between how Sprite implemented scheduling and how system V implemented scheduling. Okay. So again, here the assumption was it's a workstation environment and its owner is king, which means that a user owns their machine. Okay? So while you might want to offload work to an idle machine, you don't want to inconvenience the user of that machine. So for example, you shouldn't have a case where you go for lunch, your machine is idle, you come back and there are lots of jobs running on your machine because it took on a lot of work. Now you can't get your work done because lots of other jobs are essentially increasing the utilization of your machine. That inconveniences you as a user. Okay? So the idea is if the machine is idle, use those cycles. But when the user needs the machine, give the machine back to the user. Okay? So distributed scheduling should keep this in mind. That was the Sprite operating system's philosophy. Okay? So how does it do this? The first thing is it uses a centralized policy. That was the question that was asked. Okay, so you have a centralized coordinator that is going to keep track of load information on all the machines. Okay? No longer decentralized. One machine is a coordinator. It keeps track of which machines have what type of load. Okay? That's number one. Number two is it has again also a state change driven information policy. So basically it says that a machine is going to become a receiver if for 30 seconds there are no keyboard or mouse activity, okay, which means the user is not typing or using the machine. Okay, because you're assuming that if you're using the machine, you're typing or you're using the mouse. So if 30 seconds go by, okay, there is no keyboard input, there's no mouse input, so user has stopped using the machine, and the number of active processes that are executing is less than some threshold, okay, then we say the machine is a receiver. User is not actively using the machine, the load on the machine is low. Okay? You become a receiver and you broadcast that information to the coordinator, and the coordinator says, okay, this machine has essentially become a receiver. Okay, is that clear? Okay. So now what's going to happen? So selection policy is done manually in that the user will submit jobs to their machine, okay, and the machine might become a sender if the load is high, and then it is going to query the coordinator, okay, saying I am now a sender, I need to offload work. Is there a receiver in the system? Okay? And since the coordinator is keeping track of all receivers, because receivers, as soon as they become idle and they have light load that inform the coordinator can tell the sender saying, here is a receiver machine, offload work. Okay? So then the job is going to move and execute on that other machine. Okay? But with one important difference, which is if you offload that job and it's now running on someone else's machine, the user comes back to their machine. Okay? There's new keyboard activity or mouse activity, you will immediately suspend remote jobs. Okay? Because you say user should not be inconvenienced. That's just not that user's job. It's someone else's job that's executing on your machine. Okay? So you will immediately suspend the job and try to move it to another receiver. Because you say, okay, this machine is no longer a receiver. User has come back. They need to use their machine. So now that machine is going to suspend the job, find another machine to run it. Okay? But now you will see that this is going to require additional functionality because the job has already started executing. Okay? You're taking a partially executed job and now you're trying to move it, as opposed to all of the other policies where you took a new job and started executing. Okay? So Sprite was also the first operating system that implemented process migration, because the only way you can say the user gets back their machine, okay, is to suspend the job and move it somewhere else, or completely kill the job and restart it somewhere. But that is wasteful, because if the job ran for a whole hour, okay, and you terminated because the user came back, then you lost all of that work that was done. So it's better to just migrate the job. Okay? So that requires you to implement new functionality in the OS, which is called process migration. Okay? Process migration essentially says you can suspend the execution of a process, okay, on the machine. You can take its memory contents, okay, move it to some other machine, which is now a receiver, okay, and essentially recreate the process state as it existed on the previous machine, and magically a new process appears on this machine, partially executed, and just resumes execution. Okay? This is called process migration, not something that you will see, yeah, in the operating system, unless you're doing something with containers. In Linux containers, you can actually suspend and resume and things of that sort. Okay? But this is the first time that operating systems say, okay, we need to migrate a process. Okay? So the idea was you suspend the process, you take its memory content, okay, and you swap it out, which means you write it to a file system. The file system is a distributed file system. Okay, so now the process's memory contents have been written out to disk. Okay, and you find another receiver. Okay, and that receiver says, okay, create an empty process. Okay, and then you start paging your contents back into that process's memory. The process gets recreated. Okay, and you essentially continue execution. Okay, now there are many cases that you have to deal with. What happens to files that were being written to? Okay, you say it's a distributed file system, so all files are accessible on all machines. So you move the process, it can still access the file, continue to do I/O. Fine, okay, that you handle. And you can say, what if the machine of the process was doing network communication? What if it had a socket that was open and it was doing some TCP? Okay, this you can't deal with because the IP address of a machine is tied to the machine. Okay, so remember, the socket connection has an IP address and a port number. This you should know from lab 1 by now, right? So if you move the process, it's going to start running on a machine with a different IP address. All of its socket connections will break because anything that the other end is sending will still go to the machine with the previous IP address, not the new one. Okay? So process migration fundamentally does not work when you have network communication. If your TCP/IP connections open, process migration will simply not work unless you find another way to deal with all of the processes sockets. Okay? And we'll see how to do that later on. But it cannot be done with what Sprite wanted to. You can deal with files and I/O, but you can't deal with network sockets. And that's a limitation of process migration. Is this clear? Any questions here? Okay. Yes, question. The question is, do processes declare whether they can be migrated or not? To some degree, I think that depends on what the user wants to do. Okay? If the user knows, okay, this is just a simulation, right? Or I'm just doing machine learning training. Okay? No network communication, and you can run it. Okay? But if you have it, then you should not make the process move somewhere, because the users can decide whether the process can move or not in this case. The OS will not decide for you. Yes. Yeah. Question is, does process migration require two machines with the same OS? In the Sprite case, yes. Not only same OS, it was a Sprite OS. It can't be some arbitrary OS. Okay. All right. So that was Sprite. Third case study of distributed scheduling is Condor. Okay, this is a system that still exists today. You can download it, you can install it on a group of machines, and it will do essentially what I was talking about, distributed scheduling. Okay? So it was also designed to use idle cycles on a set of workstations. Okay? And it was used to run large batch jobs, long simulations. And the idea was network machines were precious resources. So if you have a long job and your machine is overloaded, why not run it on an idle machine? Okay? So there is a Condor master coordinator. Idle machines contact Condor for work. Condor will then assign a job. Okay? So essentially, you submit your job to a coordinator. Okay? The coordinator finds an idle job to run. Idle machine to run your job. Okay? And then when the job finishes, you get back result. Okay? And it has the same issue that Sprite had, which is the user returns to the workstation. You suspend the job and you migrate it. Okay, so essentially you can support process migration as well in Condor in order to implement that functionality. If you run Condor on an OS that does not support process migration, one of two things has to be done. You basically configure Condor to not terminate the job when the user comes back, in which case the user will see remote jobs executing and the load on the machine being high. So user will get inconvenienced, or you're going to simply terminate the job because you can't migrate it and restart it from the beginning somewhere else. Okay? One of those two things has to be true if you install Condor on a machine that does not a machine, on an OS that does not support process migration. But otherwise, you can use it with process migration as well. Okay? And you can implement all kinds of flexible scheduling policies, create groups and all of that kind of stuff. Okay. Question is, can it handle network IO? At this point, none of what I'm going to talk about today will handle network IO. When we get to virtual machines, we'll see, or containers, we'll see how to do that. Okay? But these were all operating systems or system designed in the 80s and 90s. They did not handle any process that had sockets. Okay. Fourth use case is volunteer computing. So think of this as distributed scheduling on a very large scale over the internet. Okay? All the three previous systems, V, Sprite, and Condor, scheduled jobs on a single network, one Ethernet, one Wi-Fi network, and so on. Okay? Now you can take this idea and say, let's do this at the scale of the internet. Okay? So that basically came about from this concept called volunteer computing, which was a modern way to harness idle cycles on machines like PCs. Okay? So you can assume that there are people, I mean, if you look at the internet, there are hundreds of thousands or millions of computers connected to the internet at any given time. A large fraction of them may be idle. Okay? So can you harness cycles on these machines? Okay? First thing is that you have to realize that these are machines that belong to others. Right? So you can't just randomly send a job to some stranger's machine and expect to execute it. That just doesn't work. Okay? So the only way this is going to work is that users are volunteering their machines to run jobs when the machine is idle. This is why it's called volunteer computing. You volunteer your machine saying, when I don't use my machine, I'm okay if something is running on my machine. Okay? But when I need my machine, I don't want anything else to run. Okay? So these are PCs owned by different individuals that donate CPU cycles and storage when the machine is not in use. Okay? And idling machines are going to contact a coordinator for work. Okay? And the coordinator is going to send a small amount of work and not a large job, because you cannot predict how long the machine is going to be idle. User can come back at any time. There is no process migration over the internet. Okay? So you essentially, if the user comes back and the job is running, you have to terminate it. Okay? So what you do is you take a large task, you chop it up into smaller pieces, and you assign small tasks. Okay? So that even if you have to terminate it, you haven't lost a lot of wasted cycles. Right? You can say, okay, I throw it out and I restart somewhere else. Okay? So you are going to essentially take a large parallel job, break it up into smaller tasks, assign them to PCs. Okay? Now you say, how is all this going to work? The way it works is the user who is volunteering their machine downloads a small piece of software that essentially acts like a screensaver. Okay? When the PC becomes idle, the screensaver will activate. Okay? But this is a special screensaver that essentially not only puts something on the screen, it also contacts the coordinator for some work. And a small amount of work comes, you execute it, you send back the result. If the screensaver is still running, you essentially go and ask for another chunk of work, and you keep doing these small pieces of work. Okay? And when the user comes back, the screensaver deactivates, and then whatever was running is terminated, and your user's machine is back. Okay? So you might say, why are people going to donate CPU cycles? Okay, the reason some of this came about is there are lots of applications that require a lot of compute power, okay? But they're for a good cause. Okay? So users might say, sure, I am going to donate my machine cycles for a good cause. So one good cause is, okay, you are going to essentially do drug discovery. You might say, I'm doing some cancer research. I want to find the next big drug to treat certain types of cancer, but I'm going to essentially search through lots and lots of data to find the right way to design this drug. Okay? It requires a lot of compute power. Okay? So either you are going to have to find a supercomputer to run this, or it's going to take a really lot of cycles, or you are going to depend on the good nature of lots of people who volunteered their PCs for small amounts of time and get your computations done. Okay? So there are lots of these applications that essentially take the volunteer computing route, because not everyone has access to a supercomputer to do their research. Okay? The original application that started all of this was called SETI at home, and SETI is an acronym which says Search for Extraterrestrial Intelligence. Okay? So these were astronomers who are collecting lots of radio signals on their radio telescopes. And they wanted to see if any of these signals showed any form of extraterrestrial life. Okay? Were there any transmissions that were coming from some alien planet that were being captured by them? So that literally like looking for a needle in a haystack, because you're looking at all of these radio signals. Most of them are essentially white noise. They don't have anything useful. But you're just looking for any useful pattern. So lots of work to be done. Very little good result might come out of it, because there may be often be nothing that you find in. Okay, so they said nobody is going to give you a supercomputer to do this, because a lot of your samples are just going to say nothing useful. So let's just use idle cycles that people will donate. Okay, there was the first project that started this off. Now there are lots of others that you can essentially use these volunteer computing resources for. Okay? So that's volunteer computing. It's a different form of distributed scheduling, but similar ideas. Essentially, it's a sender-initiated policy. The senders are looking for work. Okay? Yes. So first thing, let me amend what I said. It's a receiver-initiated policy, not a sender, because you are becoming receivers and taking on work. But the question that is being asked is, do you have to write your application in a way that is amenable to volunteer computing? You have to. You can't just take a random large simulation and say, do volunteer computing, because the whole idea is you are trying to do a large task, and there has to be a way by which you can take your task and make smaller chunks of it that can be parceled out. Okay? So you have to write your application in a certain way that is useful here. The other thing is, because you are running this on arbitrary machine about which you have no knowledge whatsoever, you can't even trust sometimes the result that comes back from it. Maybe the machine is buggy. Maybe the machine is sending garbage results back, because who knows? You may have hacked your screensaver, and whatever work is sent, you just send a garbage result back. Okay? So you have to essentially ensure that every computation has to be performed more than once to make sure the results match on two random machines. Only then can you trust the result, or more than maybe k times before you trust. Right? So all of this extra work has to be done for this to be effective. Okay, yes. The question is the latency a factor about which machines are near and which are far. So the latency is not as big a problem, because let's say you do 30-second or 1-minute computation. Typical latency anywhere on the network is going to be hundreds of milliseconds. So you can pay hundreds of millisecond cost and run for 10 seconds, right? So it can be amortized. Okay, so that's volunteer computing. I have a few minutes. I'm going to talk about cluster scheduling. Okay, this is distributed scheduling in today's world. Okay, so whatever I talked about distributed scheduling as it was designed in the 80s and 90s. Okay, except volunteer computing, which is actually still in use today. Okay, so how do we schedule jobs on a distributed set of machines? So first thing is, now when you do this, you essentially schedule jobs on a set of servers, a cluster of servers. Okay, you don't assume that you have to schedule them on somebody else's laptops because you are looking for idle machines. The reason is that machines are cheap. Okay? So you can, it's cost effective to just buy a group of servers and have all the users submit their job to that machines, rather than users trying to hunt for whose laptop is idle, where can I run my job, and so on. So you no longer use schedulers that try to hunt for idle cycles on other people's machines. You essentially just schedule jobs on a cluster of servers. The servers are anyway more powerful. They may have more memory, faster processors, so your job executes faster. Okay? So we'll assume that all of the modern distributed scheduling is done on servers. That's the first thing. Okay, cluster of servers. Now, there are two types of applications that you can run on this cluster of servers. The one is interactive applications, which are web services, and you can run batch applications. Whatever I've been talking about as far as the distributed schedulers go, they're all focused on batch application. Okay, they were running large simulations, or they were trying to do data processing over large chunks of data and so on. Okay? But today's cluster schedulers can also run interactive jobs. Okay, you can run a web server on a set of machines. When a web request comes in, you can send it to one of the machines and it will serve your request. Okay, that's an interactive service. Okay, so you can schedule individual web requests on a set of machines. And then you are doing the scheduling for interactive applications. You can also have a master node sending batch jobs to machines. Okay? In that case, you have a batch scheduler that's doing distributed scheduling. Okay? These are two very different types of schedulers, but both are used for from a cluster scheduling standpoint. Okay? Here's the picture to keep in mind, regardless of whether this is a web service or you're essentially running batch jobs or simulations. Okay? So we'll assume that this is your cluster. Okay? There's always a dispatcher or a master node. Okay? All requests come there, whether it's HTTP request for a web service or this is a batch scheduler, requests are going to come to a dispatcher. Okay? What the dispatcher is going to do is it is going to look for which node to send this job to. Okay? If it's a batch job, you can say, I'll wait for a worker node to become idle, and I'll send the next job to that. Right? So whenever a node becomes idle, basically it gets a job. Okay? The next job to. Now, if it's a web request, you are not going to wait for something to become idle because you want to serve it quickly. So there's a user waiting for a response somewhere. So you will simply send it to the least loaded or some such thing. Okay? So the different policies will be used depending on whether this is being used for scheduling interactive services or batch jobs. Okay? So let's look at this in a little more detail. We'll start with scheduling for clustered web servers. There's a lot of text here, but the basic concept is very simple. Okay? There are n nodes, n servers. One of them, okay, is going to be a dispatcher. Okay? That's a dispatcher. This is the pool of worker nodes. Okay? Okay? Requests are going to arrive at the load balancer. Okay? The load balancer is also called the dispatcher, by the way. Okay? So the load balancer, so here's a HTTP request. Where do I send it? Okay? So you can pick various scheduling policies at the load balancer. You can say, I can do the least loaded. The load balancer can track how much requests have been sent to what machine. So I can send it to the least loaded. That's one policy. I can do round robin. Okay? Each request goes to the next node and then you can round robin. Okay? Either of these two policies are fine. Yeah, and there are other policies like weighted round robin, all kinds of policies. Okay? So that's one aspect of scheduling. Okay? The other aspect is whether you do this load balancing at a session level or a request level. Okay? It's somewhat similar to what you did in your lab 1 when you're deciding how to send request to a server, okay, for a socket or a connection. Okay? So in request level load balancing, each request that comes in is subjected to this policy, okay, round robin, least loaded, and so on. In session level load balancing, the user's browser has created a session to this web service. Maybe it's a e-commerce applications, online store. Okay? You have an online session. Okay? Maybe you have a shopping cart. You put something in the shopping cart. So there is some state that this user has created on the application. Okay? Because maybe you have this notion of a cart. You may be logged in and so on. So if you send each request to some random machine in the cluster, that machine may not know what the state of that user's session is. Okay? So in this case, it's better to assign one node to that user session, and all requests from that user's browser are always going to be sent to that node until the session is finished. Okay? That way, if you try to look for some product and put it in a cart, that cart is memory state that's going to be kept at the server. Okay? But only one of the nodes has that state, not all of them, because that's the node that you essentially sent your request to. Okay? So you can essentially do session level load balancing, and if you have state for user, you do session level. If it's a stateless application, you can do request level. It doesn't matter in that case where you send your request. Okay, but you have to think about these kinds of issues when you do load balancing, okay, because otherwise the application will not function as you intend it to. Okay. Yes, question. Question is, are there separate clusters to do session level or request level? So this is not a cluster level issue. It is what the load balancer is designed to do. Right? So typically what will happen is each application is going to look like this. Okay? The application will say, I'm going to run on a cluster of 5 machines. Okay? 4 of those are worker nodes. 1 is a dispatcher, because you, the developer, have designed your application in a certain fashion. You know whether there is going to be state kept at the worker node and so on. So you have to pick a load balancer that is designed for what you are trying to do. Okay? So if you have session state, you have to ensure that the load balancer can do session level. Otherwise, when you cluster your application, it will malfunction. Okay? So this is essentially one application in web service, not like there are different applications running and there is a cluster. Okay? Any other questions here? Okay, so I'm going to have 1 minute left. I'm going to talk quickly about the other aspect, which is scheduling batch jobs. Yeah, so these are non-interactive jobs: machine learning training, okay, data processing, large simulations. They're all examples of batch jobs. They're not interactive. Okay, they take a long time to run. They're compute intensive. Okay? The idea is the user is going to simply submit this to a batch scheduler. The batch scheduler will find a node, 1 or more, to run your job. Okay? So if you used any of the clusters, maybe at UMass, they all run a scheduler called Slurp. Okay? That's basically a Linux, open source Linux scheduler. Okay? Slurm is an acronym saying Simple Linux Utility for Resource Management. Is essentially Linux's batch scheduler when you try to run batch jobs on a cluster. Okay? So you submit your job to Slurm. Slurm runs on the dispatcher. It maintains a queue. Whenever nodes become idle, it's going to then take your job and run it on those. Okay? But it is a very flexible scheduler, okay, in that you can configure it in many different ways. Rather than one queue, you can create a queue per group. Okay? You can create a queue for each department. Maybe there's a large cluster that UMass. You can create a queue saying this is all computer science users submit jobs to this queue. All engineering users submit jobs to another queue. Okay? And then you can tell the scheduler saying that these users get X% of the cluster resources. These other users get Y%. So you can control how each queue gets scheduled. It's no longer one global queue. There are multiple queues by users. You can assign priorities to queues. You can say there's a long job queue and a short job queue. If if your job is short, you should actually submit it to the short job because they'll execute faster. Okay? If you have a long job, you submit it to the long queue. Okay? So all kinds of flexible techniques are essentially supported by Slurm to support a large number of use cases. Okay? All of them are essentially for batch scheduling. Okay? So you can then, the policy could be first come, first serve. You can do priority. It even supports gang scheduling if you want to use this to schedule parallel jobs and so on and so on. Okay? So I'm going to stop here. We ran out of time. We'll continue this on Wednesday. Okay? So let's